Imagine this. It's a high-stakes corporate espionage case.
Oh, wow. Okay.
Yeah, picture it. 2 in the morning. An executive is on the top floor of some Fortune 500 company, entirely alone in the building.
The classic insider threat scenario.
Exactly. So they plug in this sleek, unmarked flash drive, and with just a few rapid clicks, they copy a massive database of stolen intellectual property.
Like what, product designs or something?
Right, product designs, unreleased financial projections, massive client lists, the works.
Yikes. That's a company-ending breach right there.
It really is. So once the transfer finishes, they unplug the drive, and then they drag that highly confidential original file straight into the trash, and they hit empty.
And they think they're completely in the clear.
Oh, completely. They smile, lean back in their chair, and they are entirely convinced the evidence is just gone forever, wiped clean. They think it's the perfect crime.
Right, but I mean, we both know that delete is just an illusion.
Yes, especially in the world of macOS and Linux. That data's ghost still lingers. Its name hasn't changed, the metadata is perfectly intact. It's literally just sitting there waiting to be found by an investigator who actually knows where to look.
Yeah, that data's just mapped out in a hidden ledger. It hasn't gone anywhere.
Exactly. So, welcome to the deep dive where we figure out exactly how those ghosts are hunted.
It is a totally different world once you look under the hood.
It really is. And if you are aiming for a career in IT, CIS, MIS, or cybersecurity, you need to follow, subscribe, and share this content right now.
Because we aren't just talking about theory today.
No, not at all. This is the tactical knowledge that really separates the novices from the elite investigators. Also, be sure to check the episode description right now for access to additional resources you might find really valuable for your career.
You really have to have a completely different level of understanding for this stuff. I mean, knowing how to use an operating system, that's one thing.
Right. Anybody can point and click.
Yeah, exactly. But knowing how to forensically dissect it, bypassing the graphical interface to read the raw magnetic reality of the hard drive, that is where the real power is.
Because the OS might stop showing the user the path to the deleted file, but physically?
Physically, those ones and zeros are right where they were left. They haven't moved an inch.
As an information systems expert affiliated with Tarleton State University's Dr. Sam Pack College of Business, my goal is to make sure you have the real-world tech and cybersecurity applications you need to actually succeed.
And to catch bad actors and protect corporate assets, right?
Exactly. We want to guarantee that when you testify in a boardroom or, a courtroom, your findings are absolutely bulletproof.
Which ties perfectly into what we talked about last time.
Right. So last week we unpacked Chapter 6, where we dove deep into Microsoft File Systems and the Windows registry.
We looked at how Microsoft organizes its digital house, essentially.
Yeah. But today we are transitioning to Chapter 7, which covers Linux and Macintosh file systems. Just as a reminder, this is the 7th of 15 chapters in our series based on the Guide to Computer Forensics and Investigations.
And right out of the gate, we really need to establish that investigating a Linux machine requires a massive mental shift.
Oh, completely. You have to understand how it thinks, and it thinks fundamentally differently than Windows.
It's a completely different philosophy of computing, honestly.
Yeah.
And to understand why, we kind of need to look at the family tree.
The family tree.
Yeah, because there's this historical divergence here that trips up a lot of seasoned professionals. You essentially have two main branches. First, you have the Unix distributions.
Right, the heavy-duty enterprise stuff.
Exactly, the old guard. We're talking Silicon Graphics, IRAX, SK Unixware, Sun Solaris, IBM AIX.
These are the proprietary, strictly certified operating systems that ran the massive mainframes, right?
Right. And then on the other branch, you have the Linux distributions. These are the ones you constantly encounter today. Ubuntu, CentOS, Mint, Fedora, Kali.
Kali Linux, yeah, we see that one all the time in ethical hacking. But I see IT pros make a catastrophic mistake here constantly.
I know exactly what you're going to say.
They sit down at a terminal assuming they are dealing with a certified UNIX environment, and they apply all the wrong protocols because they assume Linux literally is UNIX.
It's such a pervasive myth in the test banks and in the real world.
Yeah.
Linux is absolutely not UNIX certified.
It's just UNX-like, right?
Exactly, UNX-like.
Yeah.
Linus Torvalds created Linux in the early 90s because he wanted an OS that behaved like Unix, sharing its design philosophies and command line power.
But he built it completely independently.
Right, and it's open source, whereas true Unix is heavily licensed and proprietary. And there's another architectural reality we need to clarify here.
What's that?
When we say Linux, we are technically only talking about the core of the operating system. just the core.
Which is the kernel, right?
Yes, the kernel.
Let's make sure we define that clearly for you listening, because kernel gets thrown around constantly. If the entire operating system is a vehicle, the kernel is the actual engine block.
Oh, I like that analogy.
Yeah, it's the central translator. You have your software applications sitting on top, like your web browsers, and then the physical hardware on the bottom, the CPU, the hard drive.
And the kernel's what sits between them.
Right, it takes a software request, like save this file, and translates it into the actual electrical signals that physically write data to the silicon.
That is a brilliant way to conceptualize it. The kernel is the heart. All those other tools, the graphical user interfaces, the pre-installed apps, those were layered on top of the kernel.
Maintained by other people, usually, right?
Yeah, often under the GNU project. But the way the Linux kernel interacts with the world is governed by one overarching golden rule.
The big rule.
Everything is a file. Absolutely everything.
Which is such a wild departure from Windows. Because in Windows, you have, like, a device manager to handle your keyboard and a network center for your Wi-Fi card.
Right, they exist in completely different realms.
But in Linux, you're saying that a physical piece of hardware, like a monitor, is treated mathematically the same as a plain text document.
Exactly. Disk drives, monitors, network cards, system memory. The operating system manages every single one of them as a file. The kernel reads and writes to them using the exact same basic inputs and outputs.
Let me put this in a business context for you. Imagine a massive corporate organization. You have employees, desks, delivery trucks, right?
A lot of moving parts.
In a traditional mindset, you'd have a separate management system for each. HR manages people. The fleet manager has a database for cars.
Right, siloed systems.
But in the Linux mindset, it's like every single asset, from the CEO down to a stapler, is logged on the exact same universal master spreadsheet.
That universal ledger analogy is spot on. It creates an incredibly streamlined way to manage complex systems.
And because it's all on that same ledger, the system can use the same fundamental commands for everything.
Let's look at a concrete example. If you navigate to the dev directory in Linux, which stands for devices, you will find a file named squida.
Just storda.
Yep, /dev/srida. That file is not a text document. It is the specific stand-in file representing the first non-IDE physical disk drive on the system.
Which usually means the main hard drive.
Right.
So if I am an investigator running an imaging tool and I tell my tool to copy /dev/svuda, I'm not copying a folder.
No. You are literally commanding the software to start at the very first physical magnetic sector of the hard drive and copy every single piece of data across the entire physical disk.
Wow. You're interacting with the raw hardware through the abstraction of a file.
Precisely. And because you're interacting at that raw command line level, the realities of typing those commands can be absolutely brutal.
Brutal how?
Well, let's look at a real-world troubleshooting scenario. You have an investigator on site, adrenaline is pumping. They need to check the version of a program called sudo to see if it's vulnerable to an exploit.
Okay, pretty standard incident response stuff.
Right, so they rapidly type sudo space -v with a lowercase v and hit enter. The system just rejects it.
Because Linux is case sensitive?
Strictly, unforgivingly case sensitive. A lowercase v and an uppercase v are as different to Linux as the letter A and the number 7.
So what was the right command?
It requires an uppercase v, sudo space -V. If you use lowercase, it either rejects it or interprets it as a completely different function.
Precision is everything here. You really can't just guess your way through it.
You really can't. You need to know essential commands. Like, imagine you're called in to investigate a compromised Linux server.
Okay.
You sit down, you need to know exactly what hardware and software you're dealing with before you make a move.
Yeah.
So you type unnamed space -A.
Unnamed -A. Walk us through what that actually outputs for a business IT student.
Unnamed stands for UNIX name, and the dash a flag means all. It prints a comprehensive identification string. The specific kernel version, the system architecture like 32-bit or 64-bit.
Which is vital because that dictates what forensic tools you can even run on the machine, right?
Exactly. It also gives you the host name and the exact time the kernel was compiled. It's the fundamental identity badge.
And then your next move.
Your next move is typing IP space addera.
To map the network footprint.
Right. It lists the IP addresses and MC addresses for all attached network interfaces.
So if there's a rogue wireless adapter plugged into the back, beaming data out, IPAddr reveals it immediately.
Instantly.
Okay, I have to stop you here and push back on something, though.
Sure, go ahead.
I see a logical contradiction with this everything is a file concept. If everything is treated as a file, including a physical network card or a monitor, How does an investigator differentiate between a user's malicious text script and a piece of system hardware?
That's a great question.
Right, because if I run an automated search across the drive looking for evidence, won't the forensic tools get confused and try to read a graphics card like it's a Word document?
That is a critical distinction. It comes down to how the system organizes that ledger and flags the metadata.
Okay, how so?
Well, device files almost always live in that highly specific /dev directory. User files live in /home directories.
Right, so location matters.
Location matters, but more importantly, the system assigns distinct types to these files. When a forensic tool looks at the metadata for /dev/sudo, it sees a special flag, identifying it as a block device.
Not a regular file.
Right. Professional carding tools know to skip block devices when searching for text strings, so they don't accidentally try to carve an email out of a virtual monitor.
That clarifies it perfectly. The system categorizes the ledger entries, which actually leads us perfectly into how Linux organizes its physical storage space over time.
The file system itself.
Yeah, how does it build the house where all these files live? We need to talk about the evolution of the ext file system.
To understand the modern forensic landscape, you have to trace the engineering history.
Right, starting with XTU.
X2, the second extended file system. It was functional, but it had severe limitations with crash recovery.
What happens in a crash?
If a server lost power mid-write, the system wouldn't know where it stopped. The data could be catastrophically corrupted.
So to solve that, XT3 was introduced. And the massive architectural leap forward there was journaling.
Yes, journaling, crucial for business continuity.
I like to think of journaling like an accountant during a fire drill. Before journaling, the accountant just writes numbers directly onto the final balance sheet.
And if the fire alarm goes off and they drop their pen, nobody knows if that final number is accurate.
Exactly. But a journaling file system writes down what it's going to do in a separate journal first. It saves the metadata and its intention before it actually alters the final balance sheet.
It's an incredible failsafe. If power drops, the system reboots, checks the journal, sees it was halfway through writing a massive video file, and just safely rolls back the incomplete changes.
It prevents the file system from tearing itself apart. But XT3 started showing its age as drives got into terabytes, right?
Right. So they introduced XT4, the fourth extended file system, which is the modern standard.
So if I'm an IT director deploying a fleet of servers, what are the specific business advantages of XT4?
Backward compatibility is huge. It can automatically mount an older XT3 drive natively. No complex conversion. You don't lose access to legacy data.
What about scale?
Massively increased. XT4 supports file sizes up to 16 terabytes, volumes up to 1 exabyte, and unlimited subdirectories.
Incredible. But the way it actually structures all this data on the disk rests on 4 main pillars. Investigators have to know these pillars. First up, the boot block.
The boot block is the absolute beginning of the drive. It holds the bootstrap code, the machine instructions for startup, and a crucial test bank fact here. A UNIX or Linux computer has only one boot block, strictly on the main hard disk.
Only one. Got it. The second pillar is the super block. I like to view this as the general manager of the entire hard drive.
Manager is the perfect word. It specifies disk geometry, calculates available space, tracks block size, and keeps a master list of all the inodes.
It dictates the entire configuration. The third pillar is the inode block, sitting right after the super block, holding file metadata. And the fourth is the data block.
The data block is the vast warehouse. That's where the actual contents of the user files, like the text of a stolen document, are physically written.
Now, when XT4 came out, they fundamentally changed how the manager tracks data in that warehouse. They ditched indirect pointers and introduced extents.
Extents solve the problem of file fragmentation.
How so?
In older systems, a large video file might be broken into 1,000 tiny blocks scattered everywhere. The hard drive's red head would physically thrash back and forth trying to collect the pieces.
It sounds terribly slow.
It was. An extent changes that. It's a contiguous, unbroken area of physical storage. Instead of 1,000 pointers, an extent is a single piece of metadata that just says this file starts at block 1,000 and runs continuously for 500 blocks.
Like telling someone to read pages 10 through 50 instead of listing every single page out.
Exactly. And XT4 optimizes this further with flexible group blocks, designated by flex_big.
What does that do?
It allows the system to gather metadata for several block groups into one logical group. By clustering the map together, the system parses the architecture much faster.
Wait, hold on. You just said the super block is the master manager that maps the entire drive.
Right.
If that's a single point of failure, what happens in a disaster? like a power surge corrupts the primary superblock, does the IT admin just lose the entire multi-terabyte drive because the manager is dead?
If Linux were poorly designed, yes, total catastrophic loss. But enterprise systems are built for disaster. Linux creates backup copies of the superblock and scatters them strategically across the disk.
Oh, wow. So how do you use them?
If the primary is corrupted, an investigator uses a command line utility like Flunk to manually point the OS to a backup superblock. The map isn't lost, you just need to know how to open the emergency lockbox.
Which is why knowing the architecture matters more than just clicking around a forensic software suite. You have to know the spare copy exists.
Absolutely.
And that brings us to the core of Linux forensics, the mysterious inode. To find hidden data, investigators live in the inode block. Let's deconstruct how they operate.
An inode, or index node, is a rigid data structure. The instant a file is created, it gets an inode containing the metadata and the physical map to the data blocks.
So if an investigator isolates an inode in a hex editor, what specific evidence are they seeing?
It's an evidentiary goldmine. You find the mode and type, the link count, the user ID, and group ID, which is critical for attributing the file to a specific suspect.
And the timestamps, right? Timestamps are everything in building a timeline.
Right, the MAC times. Modification time, access time, and change time. Plus, it contains the block addresses mapping to the physical data.
But how does a tiny metadata structure map out a gigabyte-sized file?
Through an incredibly clever scaling system of pointers, the inode directly holds addresses for the first 12 data blocks.
Okay, but what if the file is bigger than that?
Then it uses an indirect pointer. That points to a new block that contains nothing but a list of more addresses. And if it keeps growing, it uses a double indirect pointer, which points to a list of pointers pointing to data, or even triple indirect pointers for massive files.
A cascading tree of maps.
Exactly. You can literally follow this cascade in a hex editor to manually reconstruct a deleted file.
But here's the twist that breaks students' brains. We listed all this metadata, but what does the inode not contain?
An inode does absolutely not contain the name of the file, and it does not contain the directory path.
So how on earth does the computer know what the file is called?
Radical separation of concepts. In Linux, a directory is just another file containing a list, a text string of the file name paired with an inode number.
That's it.
That's it. You open a folder, the system reads q3report.pdf, sees it's paired with inode 54321, and goes to that inode for the timestamps and physical location.
The name is completely divorced from the data, and that quirk is what makes links possible, hard links and symbolic links. If the physical data is a conference room, a hard link is like having two entirely separate physical doors in different hallways leading into the exact same room.
That is the perfect visual.
Yeah.
If you use the ln command in the terminal, you create a hard link. The link count in the inode goes up to 2. Both file names point to the exact same inode.
So if I delete the original file name,
the data isn't deleted. The system just removes one door. The link count drops to 1, but the data is completely intact through the second door.
the system only overwrites the data when the link count hits 0.
Exactly.
Compare that to a symbolic link, or symlink. If a hard link is a second physical door, a symlink is just a post-it note giving directions to the first door.
Right. A symlink gets its own distinct inode. It's just a text string containing the absolute path to the original file.
So it can point across a network to a different server.
Yes, because it's just directions. You can't do that with a hard link, which has to share the local inode table.
Let's tie this back to our corporate espionage scenario. A malicious insider creates a hard link to a confidential database, hides it, and names it lunchmenu.txt.
Sneaky.
How does an investigator prove to a jury that lunchmenu.txt is the exact same stolen file if the inode doesn't store the name?
The proof is in the math. Every file has a unique inode number. The original database might be inode 88402. The investigator finds lunchmenu.txt, and it is also assigned to inode 8402.
So they share the identical inode number.
Yes, which architecturally guarantees they pull from the exact same physical data blocks.
Yeah.
The names are a facade.
Indisputable evidence. Now, what about physical drive damage? Hard drives degrade. How does Linux track bad sectors?
It uses inode 1, the bad block inode. It's a permanent quarantine list of bad physical sectors.
How do you scan for them?
You use the bad blocks command, but you must log in as the root user, the super user, because it interacts with the hardware at such a low level.
But running diagnostics on legal evidence is a tightrope. You can't accidentally overwrite data.
Absolutely. That's why professionals use Mag2Fs and E2F6. They have built-in forensic safeguards to prevent overwriting important metadata during a scan.
Okay, so we've dissected the Linux world. Now we have to cross over into Apple territory.
Yes, Macintosh.
Which is fascinating because modern macOS shares a UNIs-like foundation with Linux, but has a completely different commercial evolution.
You really have to understand the Apple timeline. In a corporate environment, you will inevitably encounter legacy hardware. Before OS X, Apple used the Hierarchical File System, or HFS.
And HFS had a catastrophic mathematical flaw regarding space. Allocation block waste.
Yeah, let's explain the math. In HFS, the drive was divided into allocation blocks. But an allocation block could store only one file, no matter how small.
Okay, give us an example.
If your block size is 32 megabytes and you save a 100 kilobyte text file, it takes up the entire 32 megabyte block.
You just wasted 31.9 megabytes of space.
Exactly. It was wildly inefficient.
Like renting a 500-seat theater for one person and locking the doors. So macOS 8.1 introduced macOS Extended, known as HFS++.
HFS Plus moved to a 32-bit architecture, allowing vastly more, but smaller, allocation blocks. It drastically improved efficiency and became the standard for a long time.
Even when they moved to Intel processors and a Unix core. But in 2020, with macOS 11 Big Sur, they dropped Intel for Apple Silicon M1 processors.
And the massive hurdle for IT pros actually started in Catalina 10.15, when Apple entirely removed support for mounting legacy HFS devices.
Completely dropped it. If you plug a vintage 2005 drive into a new Monterey Mac, it just says, I have no idea what this is.
Refuses to mount it. We'll talk about how to bypass that. But first, the anatomy of older Mac files is entirely unique.
Right. It's a dual structure, two distinct parts called forks.
The data fork, which contains the raw user data, like the text or audio, and the resource fork,
where the magic happens.
Exactly. The resource fork holds metadata, application info, icon designs, menus. This is why sharing early Mac files with Windows was so fraught.
Because Windows would often strip the resource fork away, corrupting the file. But the real revolution came with macOS 10.13 High Sierra, the Apple File System, APFS.
APFS is a 64-bit system optimized specifically for flash memory and SSDs. It features nanosecond timestamps and full disk encryption.
But the killer feature every business student needs to understand is APFS snapshots.
Snapshots are a game changer for disaster recovery. It's a read-only picture of the file system at a specific microsecond, and it takes this picture without massive storage penalties.
Because it doesn't duplicate the data, it just freezes the pointers.
Right.
Frame this in a ransomware scenario. A corporate Mac gets breached and encrypted. Before APFS, you relied on external backups that might be days old.
But with APFS, an IT admin boots into recovery mode, rolls back to a snapshot taken 5 minutes before the attack, and the data is instantly restored, unencrypted.
Because the snapshot preserved the exact state of the original blocks, it's instantaneous, and file cloning works similarly, right?
Yes, instead of physically copying a 5 gigabyte video and using 10 gigs total, APFS file cloning just creates a new metadata entry pointing to the original blocks. 0 additional space used.
Basically a built-in system-wide hard link. Okay, circling back to that Catalina hurdle, if a student is handed an old HFS drive full of evidence and they only have a new Mac running Monterey, how do they read it?
They cannot natively mount it.
Right.
Dedicated labs will actually maintain a legacy workstation running macOS Mojave just for this.
And the other option?
Third-party forensic software. Tools like Incase, FTK, or Autopsy have their own proprietary file system drivers built in.
So when you plug the drive into a write blocker, Autopsy bypasses macOS and looks directly at the raw hex data coming across the USB cable.
Exactly. You need specialized tools. Which brings us deeper into Mac block architecture. How does it physically group data?
Well, any storage medium is called a volume, broken down into logical blocks and allocation blocks.
The logical block is the fundamental unit, usually 512 bytes. An allocation block is a group of those.
And Mac uses something called a clump to manage file growth. A clump is a group of contiguous allocation blocks.
I know you have an analogy for this one.
I do. It's like booking seats for a corporate retreat at a theater. If you have 5 team members, but might add 3 more later, you don't book 5 seats in row A and 3 in row Z.
Right, they'd be spread out.
You book the entire row a clump right away, just in case.
And that minimizes file fragmentation on Mac.
Yeah.
The system provisions an entire clump. As the file grows, it just occupies the empty seats.
Kept physically contiguous, making read speeds incredibly fast. Now, Mac uses two different end-of-file descriptors, logical EOF and physical EOF.
Yes, the logical EOF is the actual end of the file's data. Say you write 100 bytes, the logical EOF is at byte 100.
But the allocation block might be 512 bytes, so the physical EOF is at byte 512.
Meaning there are 412 bytes of empty space between the actual text and the end of the block.
Slack space. Prime real estate for an investigator.
Exactly. If that block previously held a confidential spreadsheet, the remaining 412 bytes might still be sitting perfectly intact in that slack space, readable with a hex editor.
Wow. Now, to track all this, Apple uses a B tree to organize its directory hierarchy.
An inverted tree structure, highly efficient for fast searches. The files are at the bottom in leaf nodes. To get there, you use header nodes for tree info, index nodes as signposts, and map nodes to keep it organized.
And the master information about the volume itself.
In HFS, it was the master directory block, or MDB. In HFS Plus, or the volume information block. When mounted, it's stored in live memory in the volume control block, or VCB.
What if a file is heavily fragmented and all the extent info can't fit in the MDB or VCB?
It gets pushed into a hidden file called the extents overflow file.
So we know how the house is built, but digital artifacts, where does an investigator look for the juiciest evidence on a Mac?
Well, unlike Linux, which uses /home, Mac stores user profiles in /user/username.
There actually is a /home directory on a Mac, though, right?
Yes, but it's purely for legacy Unix compatibility. It's almost always completely empty. Don't look there.
What about system logs?
Apple radically changed logging with unified logging. Instead of plain text files, it uses proprietary SQLite databases found in /var/db/diagnostics and /var/db/ood text.
Granular, time-stamped timelines of app execution. What about passwords?
Keychain access securely manages passwords located in /system/library/keychains. Crack the login password, and you gain access to essentially everything.
We also have to mention File Vault, Apple's native disk encryption.
Early File Vault had a critical vulnerability. The master keys were held in live RAM. You could perform a cold boot attack, freezing the RAM, extracting it, and dumping the keys.
But File Vault 2 fixed that with 128-bit AES full disk encryption.
Right. It protects the keys much more aggressively, integrating with the hardware.
Okay, a question taking us back to our corporate spy. Windows obscures deleted files in the recycle bin by renaming them, but Mac.
Massive differentiator. On a Mac, moving a file to the trash retains its exact unaltered original name. It just moves the pointer to a hidden .trash folder. So our spy drags the file to the trash, but the investigator running a tool pulls it out, and it's still glaringly titled Stolen Intellectual Property.db.
It absolutely is. And with APFS, a snapshot might have preserved the data, even if they emptied the trash.
Okay, so how do we legally and safely extract this data, the tools of the trade?
Acquisition must be forensically sound. If you alter a single byte without documentation, the evidence is inadmissible.
In Linux, the gold standard command line tool is dct4d. Why is it superior to the old dd command?
Engineered by the Department of Defense Cybercrime Center, it features on-the-fly enhanced hashing. It calculates MD5, SHA-1, and SHA-256 hashes as it reads.
Generating a digital fingerprint to mathematically prove the copy is a perfect match to the original.
It also has mandatory forensic logging for chain of custody and progress reporting, so you actually know how long the transfer will take. You install it via Kali Linux terminal, but there's a massive career-ending warning here.
The ultimate disaster. When you type the command, if equals is the input file, the suspect drive, and of equals is the output file, your blank forensic drive.
Never, ever switch the source and target.
If you switch them, you command the system to flawlessly copy the perfect emptiness of your blank drive directly over the suspect's original drive. You mathematically obliterate the evidence.
Measure twice, hit enter once. Now, Kali Linux also has the sleuth kit.
A phenomenal command line tool chest. Can analyze almost any file system. Its GUI equivalent is Autopsy.
There's also Foremost, a carving tool that ignores the file system and searches raw hex for file headers and footers using foremost.conf. It can pull a JPEG straight out of Slack space. Paladin Edge is also a great Ubuntu-based option.
But while Linux is a software challenge, modern Mac acquisition is an absolute physical nightmare.
Nightmare is right. Apple doesn't want you taking their computers apart. Proprietary pentalobe screws and flash storage chips soldered directly to the logic board.
You can't physically remove the drive, and if you try to read the chips directly, the T2 security chip hardware encrypts it into high-entropy gibberish.
And for Apple Silicon M1, M2, M3 Max, it gets worse.
To run professional Intel-based imaging software, investigators frequently must install Rosetta 2, Apple's translation layer. And to do that, you need the system administrator password.
Wait, hold on. The golden rule is never alter the original device. But you're telling me I have to boot the suspect's computer, log in, and actively install software directly onto the evidence drive just to run my tools? How is that admissible?
It's a massive point of debate. The industry justifies it through the doctrine of necessity and exhaustive documentation. You document the exact hash value of the software, the exact second it was installed, and map the affected sectors to prove you didn't touch the actual user evidence.
Incredibly risky. You also have to battle disk arbitration?
A macOS daemon that automatically mounts and writes Spotlight indexing logs to any connected drive within milliseconds.
So investigators use live boot tools like Celebrate Digital Collector or Sumiri Recon ITR to specifically disable disk arbitration before attaching evidence drives.
Or they boot into macOS recovery mode by holding the power button, downgrade the startup security utility, and boot to a trusted forensic USB.
But you still need the custodian's credentials or you're locked out.
Always.
Okay, let's synthesize this incredible journey. We covered the Linux philosophy of everything as a file, XDEF4 journaling, extents, inodes, and hard versus symbolic links.
We crossed into Apple, going from wasteful HFS allocation blocks to APFS snapshots and contiguous clumps.
And wrapped up with acquisition tools like DC3, hashing, logging, and the absolute nightmare of Apple's soldered hardware, T2 chips, and Rosetta 2.
Deeply understanding this architecture is what makes you an invaluable asset.
Going back to our corporate spy, the ghost was always there. The evidence never left. You just had to know the architecture of the house it was hiding in.
The ones and zeros simply do not lie.
If you found value in this deep dive, please hit that like button, subscribe, and share this with your fellow business and IT students. Check the description for additional resources and review our channel for more playlists and videos to help you continuously learn.
Continuous learning is your only actual defense in this field.
Join us next week as we move to Chapter 8, Media Files and Digital Forensics, where we'll look at steganography and how data is hidden inside image and audio files. But before we go, a reflective question for you.
Think deeply about this. As Apple and Linux push encryption deeper at the hardware level, we are losing the ability to physically remove a hard drive for sterile lab analysis. How will digital forensics evolve when we are forced to rely entirely on interrogating live, running, potentially booby-trapped systems?
That's a wrap on this episode of Digital Forensics. Until next time, analyze the copy, preserve the original.